This is our second week of review and foundations, and then next week we move into moderation. So far, has anyone thought about data sets or questions you might want to work with as you move through the workshop? So this is, yeah?
I have a data set. I'm not sure if it qualifies for mediation. I'm doing regression though.
Okay.
If you, I can describe it.
Yeah, I mean, describe maybe the mediation questions you were considering, and it could be moderation questions as well.
So what I know, okay, so what we have is, it's a set of 205 people.
Mm-hmm.
Let's see, how many, like 130 of them are healthy controls and the rest are bipolar.
Mm-hmm.
They range in age from like 7 to like 26, so there's age in there obviously continuously. There's obviously the gender, and then there's, we have an IQ measure of full IQ, seek-based, and then 2 neuropsych tests. One of them is like a spatial working memory test, and the other one's like a problem-solving test. The variable of interest is reversal learning. So doing a task, getting rewarded in one direction, and then having to reverse, and like now learn that the other one is the rewarding thing.
Okay.
So maybe some of those other things that I described first might moderate or mediate, or any, I don't know that well, that difference, because we know there's a difference in bipolar. They're worse at doing this reversal task, and then on the non-reversal stages they don't show a difference. So I don't know if that's useful. I just know that I just figured I'd throw it out there.
Yeah, that's great. I mean, I sort of understand that the
Yeah,
variables you're
that was
talking
like
about.
A one-paragraph version of it.
But we can assume that group of bipolar versus non is going to be the independent variable. You said this performance on reversal learning is the outcome variable,
Yeah.
and then the question is, are we thinking about individual factors or between person factors that would, like you said, moderate how they perform on that task versus some type of process through which their performance was affected.
Yeah.
And I wasn't sure if it sounded like you had those types of variables in the data set. So
Yeah.
like intermediate processes.
Well, so I think that like spatial working memory, like spatial span, might help you do the task, because it might help you work, like it's an index of working memory. So you have to remember which thing was rewarded and remember which thing you chose and all that stuff.
Right.
And the problem-solving measure is just like ability to plan out. So I don't know if that is necessarily relevant.
So in the problem-solving measure, you could then, I guess, assume that might differ between bipolar and non.
Oh, they all do. Yeah.
They all differ.
Yeah, spatial span differs, and the working memory thing definitely differs. Both of them have simple t-tests. They both differ.
Okay.
Yeah.
That sounds great then. That
Okay.
sounds like a great potential example, and you can think through to maybe even like moderated mediation if you think that makes sense.
So I don't actually.
Because we'll go through all of those examples.
Okay. I don't know. I actually don't even know what that means. So.
Meaning, does the mediated process hold for under certain conditions and not others for that group? So say it's, the mediation process holds for bipolar individuals. That's what we think, right? But is it certain types of bipolar individuals? That would be an example question.
Okay.
Yeah.
And it's a range in age too, between 7 and. Yeah.
Age is a good example of a potential moderator of the mediating process between the two diagnostic versus non-diagnostic.
Okay.
Good. I'm glad.
Yeah.
Glad. What about other people in terms of digging around in their data sets or mentors' data sets and thinking about stuff they could bring in or stuff that they could work with after class to then bring in their output and bring in their interpretations to class as we work through the examples of the different aspects of the course we're working on. Yes. There's that enthusiastic hand. Yes.
Right here.
Yes, so last week it sounded like a straight regression example.
Right.
Can you remind us of it? Because it was over my head, the variables.
The study
again.
is giving IV, so this is the relationship between 2 feeding hormones.
Two.
feeding hormones,
Okay.
and how they actually relate to craving for alcohol.
Uh-huh.
So this is gut-brain effect.
Okay.
So we gave IV ghrelin, which is give the sense of appetite.
Mhm.
And then we monitor how leptin, which is the opposite hormone, would have an effect. And how the regression between those two hormones affect then craving,
Mhm.
for specific for alcohol. So we have assessment for craving for, was targeting the signal for alcohol and targeting the signal for food. In this specific case was juice.
Mm-hmm.
And then we see a response. We see a response, and there is an effect. So ghrelin goes up, leptin goes down, and cravings goes up.
So is leptin then potentially a mediator?
Exactly. So leptin can be a potential mediator.
Okay.
Then the other things are that I would like to put are things like glucose level at baseline. Does actually the glucose level would affect either, or even ghrelin that was given exogenous, but also the endogenous effect of leptin. Or the other thing could be the age of onset of alcoholism, because we measure craving for alcohol. So it could be that one, and that could be continuous variable for to measure as a mediator. Gender, and the reason is because, and then the other one could be BMI, because both ghrelin and leptin are secreted by adipocytes. So is the BMI affect the secretion of leptin, especially during induction, like of exogenous or ghrelin? So there are many, it's a busy one.
Yeah, a lot of options.
Yeah.
And then remind me the sample size again?
The sample size is small because this was a lab study. So we have 18 on placebo that we give it just saline. And then we have a dose of 14 and 15 for 2 different doses of ghrelin. But they already run an analysis and it's not dose dependent. So the 2 doses can be collapsed together. So we have about, let's say 18 and 25.
Okay. So that's going to potentially limit what you can look at in terms of sample size, but still worth a shot and definitely could, help you conceptualize through the examples that we're working with.
Yeah.
It could, that for moderation and for mediation, it definitely, those are relatively small.
Yeah.
But you have your grouping variable, and then your outcome variable, and then it sounds like at least 2 potential mediating processes, and then a whole host of potential moderating processes.
Yes.
Yeah. Does that make sense to everyone? Like the 2 examples so far, basic idea? Yeah. I wonder if it would be useful for you guys actually to maybe like send me like a, independent variable, dependent variable, selection of mediators, selection of potential moderators, model you're hoping to test. I could either, I can definitely post them then for everyone to see, so that we can, when we're talking through the examples, we have all the variables and the kind of basic concepts in mind. Does that sound okay? So if you email it to me, I'll post it, and then once we're talking about your output, it'll help everyone else keep straight, like, okay, this is the example we're working with here.
Yeah.
Yeah?
Mm-hmm.
Okay.
Do you want the output or like a figure? I have a figure of like what I want to.
Okay, so tell us what you want to test.
So it's part of my dissertation data. I'm looking at sustained attention, so self-report measures of sustained attention. The outcome is post-traumatic stress symptoms on the PCL, and I'm looking at experiential avoidance as a mediator between those. So the IV is sustained attention, the mediator is, it's a very simple model, experiential avoidance, and then PCL scores.
Okay, so that sounds so
It's pretty simple.
experiential avoidance.
Yeah, it's I'm using the AAQ, the acceptance. What is it?
An action question.
Yes. the acceptance and action questionnaire. It's a small, like 7-item.
So avoidance symptoms mediating the relationship between, remind me of the independent variable again.
Sustained attention.
Sustained
So self-reported
attention.
sustained attention and PCL, PTSD symptoms. So this is among a web-based group of women who had been sexually abused. Or
Okay.
sexually victimized.
Okay, good. That sounds good too. So yeah, a figure's fine. A figure's great, and then just those main variable names, kind of, you know, like in layman's terms, rather than the actual variable name that's going to be like DZAT or whatever. What about other people? It's great that we have 3 examples to talk about, because it's just going to be less of me just kind of like lecturing through the slides and more like of a workshop experience of, like, you know, working through the examples together. Did you have something, or?
I could do it.
Yeah, let's hear it.
I guess one paper I'm working on is looking at the effects of discrimination on depression for
Mhm.
Black males,
Mhm.
and looking at how self-esteem might mediate that relationship. So discrimination predict lower self-esteem, which would predict more depressive symptoms. And then I'm going to hopefully look at moderated mediation, looking at ethnicity differences. So for being Afro-Caribbean Black male as opposed to an African-American Black male.
Mhm.
That process is different for
And
those ethnicity groups.
And do you, what's the sample size in terms of
The
the
population level samples is like
huge?
yeah, like 1,000 African American Black males, and 1,000 Afro Caribbean.
So it's possible. So you can look at the moderation then. That's
Yeah.
great. That's really great. All right, good. Any thoughts or questions from last week? All right, this is where we were, right? We were talking about the best fitting, kind of conceptualizing the best fitting regression line as the goal of the model solution, finding it. What does that mean in words? It means that it's minimizing the difference between the observed and predicted Y values, and it's the predicted Y the predicted Y values based on the parameters that are derived from the model. This distance is observed Y versus minus Y hat, which is the residual, and the sum of the residuals is 0, and that's why we square the sum of the residuals, right? Because they're going to cancel each other out. There's going to be some positive residuals, and there's going to be some negative residuals, meaning, you know, above or below the line of 0. To construct the line, we begin with the predicted mean for Y when X is 0, right? So this is the intercept. We attempt to explain further variability than explained by the intercept, and we see that as the constant in the output, by adding a combination of linear predictors, right? So we're adding in those X's to move the regression line from just what we would be predicting, because I can't draw it, so I'm going to do lots of arm movements. What just will be predicted by the intercept, right, the starting place, to, you know, a line that is going to minimize the difference between all of those observed points, right? Minimize, minimize this distance here, right? Okay. The predicted Y for the sample is the best fitting linear combination of the X parameter values that move, that's what I just said, that move the regression line to the intercept, from the intercept to the best fit. Okay, so today we're going to talk about assumptions and running through some basic assumptions and diagnostics, and then we're going to go through the regression output and just kind of crunch the numbers in terms of, like, here, this is what it all means. And then we'll just talk briefly about options for variable entry methods. So that's the 3 basic topics for today. So in terms of regression assumptions, the core assumptions that we think about are linearity, right? The relationship between the predictors and the outcome variable is a linear relationship. We also think about homogeneity of variance, meaning that the area of variance is constant across the predicted Y values, right? So that means that when you have when you have the regression line, there's the variance is kind of the same shape, maybe like we could think about like an oval or a football, right? In terms of what's left, the error variance. In terms of model specification, the model should be properly specified, and that just means that's something that we can sort of address, which is we have included all needed variables and we don't have any unneeded variables, right? Other issues that we might check for would be influence, so individual observations or outliers that exert undue influence on the regression line and the model solution. And then collinearity, so predictors that are highly collinear can cause problems to the estimation of the regression coefficients. So if you have a lot of collinearity in the model, you can destabilize the regression coefficients, meaning that they start doing kind of strange things like flipping signs, or you can upwardly bias the standard errors, meaning that you lose power and you get non-significant effects. So those are some things that we're going to talk about checking for. So in terms of analysis of residuals, this is the main approach to checking a lot of these things. Error in the observed value is the deviation from the observed value from the true population variable. So just a difference in definitions. It's like when we say error, we're talking about populations, and when we say residual, we're talking about observations. We're talking about the regression model, right? The specific, the sort of proxy of the population error, which is the residual from our sample. The residual of an observed value is the difference between the observed value and the estimated value that is estimated from your sample data. So I just said the same thing, two different ways. Residuals provide the basis for assessing the adequacy of the model in relation to the population. And when we say in relation to the population, we're saying in relation to those assumed population characteristics, right? So we're saying in relation to the assumptions of the model, okay? Does that make sense? All right, so certain features of the residuals are diagnostic of violations to assumptions or other flaws in the model. So we're going to talk about nonlinearity, outliers, heteroscedasticity, and actually we'll talk about collinearity as well. So in terms of nonlinearity, instead of a uniform band of positive and negative residuals from low and high values of y, we observe that, say, positive residuals will predominate at low and high ends, and then negative residuals will predominate in the middle. So that's a U shape for the band of residuals, right? And this implies the predictor has a curvilinear rather than linear relationship to y. So who works with nonlinear, like adding quadratic terms to their models? Can you talk about it?
I've used age before,
Mm-hmm.
which was a long time ago. So we were looking at different socioeconomic factors and how they predicted reading and math outcomes, and so age ended up being quadratic in that equation.
Okay, and so age, how in terms of the relationship, so age predicted increased reading and math scores to a certain extent, and then, so when we're talking age, we're going all the way up to 100.
Mm-hmm.
Okay, so you learn reading and math to a certain extent, and then you start losing that relationship that positive relationship between age and your academic performance or your intellectual performance. Okay, good. It's a good example.
I've tested nonlinear models, but the linear ones in the cases that I've worked with tended to be the best fit. So it ended up with a linear model, but I have experience testing like quadratic and exponential effects.
Mm-hmm. So say that again.
Oh, sorry. So I raised my hand because I've run analyses where I really wanted to look for nonlinear models, but they haven't ended up being the best fit for the data.
I see what you're saying. Right. And so then what would be an example of what you thought was going to be a nonlinear model?
So I had, this was an eye tracking task that had a learning component to it. So I was tested across blocks of trials to see if the kids got faster, and so I expected there to be kind of like a plateau towards the end, and it was pretty much a linear function. So.
And you saw that visually as well as in the non-significant quadratic term.
Yeah, I mean, it looked like it could have started to be quadratic, but it just wasn't. There was also a power issue with that model.
So small sample. Okay.
But so like the quadratic effect didn't quite come out.
Right. But that's something to think about.
Yeah.
Right, in terms is sample size in terms of fitting that nonlinear model, right? You're adding a predictor, you're also adding an interaction term, right? Okay, so what do you do in these cases? You revise the model to account for that nonlinearity, such as most often adding a quadratic term, meaning just adding that variable times itself, or said another way, that variable squared, okay? The goal here is reduction in the variance of the residuals, meaning the goal is just to have a better fitting model, right? If you're assuming a linear model, it's not a linear model, you're going to get a better fitting model if you fit, you know, that curvilinear effect. So here's just a couple examples. So of a positive curvilinear relationship, we can think about, I think about at least ceiling effects of treatment. Right? So coping skills training will increase self-efficacy to a certain point, and then there's a certain point where you're not going to get a dose-response effect of that treatment intervention any longer. Right? So it's not necessarily that you get a full, we can call this an N-shaped curve. It's more that you're going to get a plateau in the effect of your intervention. Right? And then in a negative curvilinear, the thing that I always think of the most is the infamous check mark of treatment effects. So this is where actually we're thinking more in terms of a longitudinal model. So you've got drinking reduces over time to a certain point and then returns to baseline. So there you actually could be getting more of a full curve, right? So this is your drinking reduction, and this is, say, your months of follow-up over time. So it's going down, everyone's doing great, you're so happy. And then at a certain point, depending on the treatment, 6 months, could be 3 months if you're talking about the control condition. At a certain point, they're going to start going back up again, and they may return to baseline. Make sense? Yeah. This is just looking at it in terms of what it would be in the residual, what it would look like in the residual plot. You can look for nonlinearity just from an observed plot, but in this example, this is a residual plot. So you have predicted Y here, and then studentized residuals here, and the studentized residuals is just standardized residuals, right? And you standardize them to allow you to be able to potentially detect outliers once you've standardized the variance between all of the points. Okay? So typically when you're looking for a nonlinear effect, you're going to run studentized residuals with predicted Y. You can look at it in other ways though. So in terms of outliers, so are there any questions on that? In terms of looking for outliers, outliers are far out observations, and that means extreme residuals. They could be either positive or negative. So when we look at this picture, we don't really see any. So this is not a good example. But when residuals are standard, this is what I said, when residuals are standardized, meaning a residual that is greater than 3 standard deviations units outside is reasonably considered an outlier, right? So because the regression minimizes the squared residuals, an outlier is not only going to make a large contribution to the variance of the residuals, but it's also going to pull on the slope of the regression line. So it's going to, depending on your sample size, exert a relatively strong effect on the solution that you get for the model. In some cases, the outlier will alter the distribution affecting significance tests. So what does that look like? Here's this is sort of a perfect example. A regression line without the outlier, right? So we see that the intercept is around 104. We've got a negative relationship, so a negative slope parameter of 4.1, and a regression, a variance explain of 0.94. So we've got almost a perfect fitting line here. If we had just this one outlier, it is going to move our slope down lower to 97. It's still a negative relationship, but we've got a reduced magnitude of the parameter, right? So the slope is a little less steep. And because of that, because all of the residuals are now spread out further from the regression line, we've got a lower variance explained. In fact, a substantially lower variance explained. Okay? So, outliers are, I want to hear your thoughts on outliers. They're controversial. What do you do with them, right? Like I said, if you have a large random sample, maybe they're not that much of a concern. They're not actually going to have a strong effect on the regression model, and you can just leave them in there, and they'll just sort of chalk it up to random noise. When the sample is small, an extreme score is going to have a large effect. You can diagnose outliers with a statistic called Cook's distance, and this can be used, this is used to detect outliers that are going to influence the predicted Y value, right? So it's going to calculate a score for each individual predictor, telling you this is how much predicted Y changes with this outlier removed, okay? Values, the rule of thumb is that values are greater than 1 are considered potentially influential. So what do you do then if they're considered potentially influential? What do you do with them? Do you drop them? You could, if you felt, this is where it's sort of more of like an art, this is an art than science thing, this is theory, this is, knowing your study and what could have happened. Potentially you drop that outlier if you feel that this is clearly keystroke error on the part of the research assistant. You say something?
Well, so in my actual data set, I had one person that was 30 years old, and the next highest person was like 26. So I don't know if that person's an outlier, clearly, right? But I feel bad dropping them just because they happen to be 30 years old.
So what's the age range in the sample?
The age range is 7 to 30, but there's only one 30-year-old. So I drop the one person and it changes the results.
Does it change the results?
It makes the age effect that's independent of diagnosis go away. So it's that one person driving that result that's sort of bad, right?
But so what's the sample size again?
The sample size is like 205. Or 208 with the approach, but yeah, so 206.
So, and do you have reason to think, though, that this difference between 26 and 30, or so like how many people do you have that are like, say, 24 to 26, or like,
Pretty continuous, other than that one person.
Right, so do you have reason to believe that this difference would change a relationship?
I don't know. I doubt it. It's just the fact that it's driven by one person seems to be a little troubling.
Right.
But I don't have a very principled reason to drop them necessarily. Just that they're 30 versus 26 versus 7 years old. The other end is 7.
What's
right.
the outcome?
What?
What's the outcome?
The outcome is that there's an effective age independent of diagnosis.
Maybe that's the dependent variable.
Oh,
Yeah.
sorry, the dependent variable is that reversal learning task. So, a 30-year-old might be a lot easier, might have a lot easier time on the reversal learning task than a 20, I don't know, but the 26-year-old should have an easy time too, right? You'd think. So it's a bit weird to drop the one person, but it also makes the effect go away.
But is the effect something that you would expect to happen?
Yeah, because I would expect an age effect just independently of diagnosis, given that it's a task that's kind of hard to do for a 7-year-old and easy for a 30-year-old. And you must can do it really easily, but a 7-year-old has trouble. So it's just that's all. I'm just asking that,
Yeah, I'm not sure what I'd do with that situation. One thing that comes to mind is maybe is turning age into groups.
When you do
And
that, you just it cuts down the, it's because it's arbitrary, right? Like
is it
18
arbitrary?
Well, 18 years old is a very arbitrary age in terms of brain development.
So meaning that you couldn't create 2 or 3 groups that would be meaningful to test this age effect and kind of to test an age effect that would be meaningful. Meaning, what are you going to tell the people that are reading your study, about this age effect? Why is it important?
I mean, it's an effective development. I don't know. I mean, I see cutting it like it's very arbitrary to cut like.
Well, can you cut them at developmental age groups? So,
Right.
I don't know, child adolescence, emerging adulthood, right? So there's developmental theory on emerging adults being 18 to 20, as far out as 29, yeah.
Right. But what's the
So-
difference between a 17-and-a-half-year-old and an 18 something? It's just I mean, really, I have ages of like literally the days. Like days, like the number of days old they are, percentage of year. It's like I have the date of testing and the date of birth, and it's like very continuous across the entire age range. So feeling like I feel cutting at 18 is very arbitrary.
Well, can you cut at like 20?
But how is that less arbitrary?
Yeah,
And
I mean,
so-
it's less,
I don't. I'm just
yeah.
saying. I'm sure there's nonlinear effects in that
Yeah,
too. Because
but
ages.
I would suspect your issue is not that it's simply an age, and frankly, 30 versus 26 and a distribution from 7 to 30 is not numerically it's not that big an outlier.
Mhm.
My suspicion is that you either have something else in the model that's a proxy for age, and if you simply delete one case, you may be, disappearing effect. It's also a matter of, is it, you're going from 0.06 to 0.04, p less than 0.06, or is it
No, it's
it's a
like
huge difference.
it's significant to
And
non-significant.
then the other thing to look at is whether this 30-year-old is an outlier on your reversal response. That may be where the problem is, that it's not that you've got a 30-year-old, it's that you've got an outlier on
I
the
think that's what it is.
reversal response. And if that's the case, it's probably just coincidence that it happened to be a 30-year-old, could have been one of your 26-year-olds or
Right.
22-year-olds, was just someone who's particularly good at it, obviously,
Mhm.
because otherwise it would totally fuck everything up.
Yeah. So they might have a high Cook's distance because they'd have a big residual in terms of all the variables put together. Is this Cook's resistance, is that in terms of all the predictors together?
The change, yes. You meaning for the full model,
Yeah.
full model, yes.
Yeah. Okay. So then maybe that's why I should check the Cook's distance and see if it's high.
Yeah, the other thing to keep in mind is even in a sample of 200, when you get a significant association, it's not because 200 cases are lining up, it's because a few cases at the end of your distributions are lining up. Because we don't work with correlations of 0.8, we work with correlations of 0.3, and when you plot that, visually it's not a whole lot different from a correlation of 0, so it's just only a few people on the edges to
Yeah.
get you away from that horizontal line to something with a slope.
Okay. That's helpful.
So I would really look at that case in terms of everything that's in the model, and I would also ask yourself the question, is there something else in the model that's proxy for age, that's eating up the age variance, that would otherwise allow that age effect to remain in place? But it sounds like you may just have not an age outlier, but a reversal learning outlier.
Yeah, reversal learning is also discrete. It's like you can only make so many errors, right? It's not like you can make 2 errors, you can't make 2.5. So, and there's also a floor effect on how many errors. So it may not be a formal outlier in terms of like.
Well, you may have a distributional issue.
Yeah. Okay. Thank you. Sorry.
No, that's
Yeah.
that's
no,
good.
but that's really the crux of all this. What do you do when you have outliers? You don't want to take a case away and you try to fix the problem in a way that doesn't either systematically bias your data or lose the integrity of the data.
Right. Yeah. Thanks.
So I'm sure Molly's going to say a few things besides dropping cases.
There are other things you can do. You could, and it really depends on your theory, how you understand, like how you understand who this person is, and how you find out about who this person is going to be running a lot of, there's that Cook's distance, but there's also just running a lot of descriptive statistics that could then potentially diagnose something like that person being an outlier on their performance rather than on their age.
Yeah.
So recoding to within one or two of the sample distribution, or recoding in one or two standard deviations, or you could recode into the next highest or lowest value. In this example, that doesn't sound like a good option. Run with and without that case and report both. You're going to have your primary analyses, and then you'll have some sensitivity analyses that potentially you would put in a table note or in the results themselves. Rescaling X or Y, so doing transformations. Try potentially, I think the last or least potentially useful will be trying a nonlinear model. Okay? But bottom line, really thinking about who is this person, or these one or two people. Heteroscedasticity. The variance of residuals are assumed to be constant over the range of predicted Y values. Right? There's not necessarily assumptions about the shape of the distribution for X, but the shape of the distribution for X would be important in terms of interpretation. And that just means that if X maybe has any extreme distributional properties, like say you have, an X value that is a very rare occurrence or something like that. When the scatter of the residuals is not constant over the range of predicted Y, then we have two main considerations. The validity of the significance tests could be affected, right? Because the significance tests assume that constant error. And the total error variance might be larger than it really needs to be, or larger than it could be with a better fitting model. If the variance is stabilized, a new model will have a better fit with the data, and that will be evidenced by an increase in the R-squared magnitude. So here's just an example. So this is the homoscedasticity. Homoscedasticity, under the conditions of homoscedasticity, so constant error variance, versus seeing that sort of fan shape is essentially telling you that you have a poor prediction on one value, on one range of Y values or another. So in this case, we're talking at a high Y values. It could be the opposite effect, though. So the model will be often be greatly improved by simply rescaling Y. You could do doing like say a log of Y or a square root of Y. Sometimes you could do a transformation of the X variables as well. Then I just added some general guidelines on transformations of variables that I looked up in terms of like, okay, what are the best practices under certain conditions? Square root is generally good for moderate skew versus a log is generally good for more severe skew. We use exponents for curvilinearity. When variables are percents of proportions, we can use an arc-sine transformation. You can transform X or Y or both. But generally, you're attempting to normalize Y or linearize the XY relationship, and that's going to help bring you toward achieving homoscedasticity. But this is generally a trial and error process, right? So you're going to try maybe out a few different transformations and then recheck those plots, see how the R-square value is affected before you decide on the final transformation or the final approach that's best.
Would arc-sine work for counts? Because you say proportions and percents, but what about count variables?
I don't know. Does Ron know? Arc-sine for counts?
I think it all depends on how the counts
Are distributed,
are distributed.
right. It's,
Yeah.
are they distributed?
I gotta say, I've never had an experience in my lifetime where a data transform has been useful.
Really?
Yeah,
Never was.
I wondered about that too.
In terms of, I mean, yeah, you can make the distribution look a little better, but I've never had the experience where it mattered at the end of the day whether I did it or not and whether it helped. I tend to think about either using ordinal measures or using distribution-specific analysis methods when the distributions are bad enough, and if your sample size is big enough, the distributions rarely get bad enough.
Got it.
So I'm not a big transform lover, so don't ever ask me questions about whether this one works.
Okay. But I think the rule of thumb would be to try a couple of different things
Okay.
and compare them. Because, you know, if a particular, are you a treatment researcher?
I occasionally have treatment data analysis problems, yes.
Yeah, so, I
And
mean,
yeah, you're
so
gonna
you
see it
do,
local, yeah.
yeah, okay. All right, that's it. Yes,
Yeah, could you please go to this slide?
this,
The percent, no, the other one. For the percent analysis, what's ERCSM?
arc sign
Or
transformation?
the arc sign?
Yes, yeah, so these are,
No, I don't
I think these are I think these are actually SPSS, you know, transformation.
Transformation,
Yeah.
Yeah, not, okay.
All right, so here's an example. This is an example of looking at alcohol expectancies in relation to the perceived costs of cutting down drinking. This is a small sample of 47 heavy drinkers. The bottom line is that the expectation would be that those with stronger beliefs about the positive effects of alcohol would also think that the costs of changing their drinking are higher, right? So we're expecting that positive relationship. So here's an example of the SAS code for the regression model. So you run prop reg. Here's the model statement. The dependent variable is here, the independent variable is here, and these are just a couple of options, right? So asking for standardized regression coefficients and asking for the semi-partial R-squares. I have for here, instead of having a list of what diagnostics I'm looking for specifically, in SAS you can ask for a default set of diagnostics that is more information that you're going to need. So I would recommend just using that. Versus with SPSS, which at the end of the slides there's an analogous example for SPSS, and to my knowledge SPSS doesn't have that same option, although I haven't actually ever looked for it. So in the SPSS syntax, the individual the diagnostics are asked for individually in the syntax, and I can show you that when we get to it. This is just a reminder of our formulas. And here we have our output. And so in this first piece, and this is SAS output, right? So in this first piece, a couple things that we want to look at is the degrees of freedom. Right, so the degrees of freedom for the model versus the degrees of freedom for the error. The degrees of freedom for the total model is going to be the n-1. For the model, we have the parameter, the number of parameters -1, which we have 2 parameters because we have the intercept and then we have the coefficient value for positive alcohol expectancies. And then in terms of the error variance, it's 47 minus 1 minus 1, which is the n minus k minus 1, equaling 45. The variance accounted for in the model is the sum of squares for the model divided by the total sum of squares. So looking at the above example, what we've got here is these two values, which give us the R squared value of 26% variance explained, okay? And then the mean squares regression divided by the mean squares residual is what gives us the F value, okay? So if we were to crunch those numbers, these two numbers here, that's where we're getting our F test, okay? I tried to go through and pretty much define like every single thing that was on here. So the R squared coefficient, that is, as we know, the proportion of the dependent variable's variance that's shared with an optimal combination of one or more predictor variables. In this case, we have one, right, which is that the positive alcohol expectancies. Above we see we've got 26% variance explained. So 26% of the variance in the cons of drinking reduction, right, or the perceived downsides of changing your drinking are explained by those positive expectations about the effects of alcohol use. Oh, just also noting that the semi-partial correlation right here is the same as the R squared value because there's no other variables in the model, right? So we're more interested in this when we've got a multiple regression model so that we can be looking at unique effects, unique estimates of variance explained. The adjusted R square is really adjusting for degrees of freedom. So it might be something that you would use when you had a smaller sample size. That's that. Okay, so then going down to the parameter estimates, right? That's our model solution here, and then the individual parameter estimates. The intercept is when the line representing the best fitting estimation is the intercept represents the point at which the regression line crosses the y-axis when x equals 0. So if we were to center the x scores, the intercept would then be estimated y when x was at the sample mean. And we're going to talk a lot more about centering next week, when it's useful and when it's not, may not be useful or may not have a point to it. But often it can be helpful in changing how you can interpret the regression coefficients. The regression coefficients is the amount of change in y per unit change in x. So for each unit increase in positive alcohol expectancies, we expect a positive change of 0.023 in cons of drinking reduction. And so if we were to estimate an individual score, right, for cons of drinking reduction with a person who had positive expectancies of 50, this would be, we take our intercept, which is our starting value, and then plus 0.023 times 50, which is that individual score on expectancies, right? So the individual score on the x value equals their predicted value for cons of drinking reduction of 1.8, which the scale was 0 to 4. The expectancy scale was something like 10 to 100 or something like that. Okay? In terms of the standard error, it provides an index of sampling variability around the regression coefficient. You could use it to create confidence intervals. This is how we're getting the significance test, the t-test for the significance. Is the regression coefficient significantly different than 0? So we're getting it by dividing it by its standard error, which is going to give us that t-value, okay? Which if we looked it up, that's the p we would get for that t.
What are the degrees of freedom associated with t?
That is just going to be the k minus 1, which is number of predictors minus 1.
Oh, okay.
Standard errors of the estimate decrease as variance accounted for and degrees of freedom increase. So the standard error could increase with greater multicollinearity with other variables in the model. So you had multicollinearity in a multiple regression equation. In terms of standardized regression coefficients, the standardized regression gives us a measure that's standardized, so this is would be more of interest when we had a multiple regression model, so that we could compare the magnitude of the predictor variables across predictors if they were on a different scale, if you had, several X variables that had a different scale. The interpretation is for every increase of 1 standard deviation in positive alcohol expectancies, one would expect a half of standard deviation unit increase in the cons of drinking reduction. So that's here. So that's what I have for the output. Are there any questions on the regression output? So just to review, I think it's helpful to go through and kind of do the math a few times just to get a sense of exactly how the model's operating. We're going to do that a lot when we get to mediation. Okay, so multicollinearity and tolerance. Tolerance is a measure of how much variance of each predictor is overlapping with other variables in the model. Tolerance ranges from 0 to 1. The values closer to 1 indicate that the variable has a relatively higher tolerance, right? So most of its variance is not shared. And the rules of thumb is that essentially above 90 is what we're looking for in tolerance values, and below 70 is when we might start having some concerns about multicollinearity or collinearity for that specific variable. So here's an example of where we've added in age and we've added in perceived benefits of drinking reduction, and then we still have our alcohol expectancy. So these are their tolerance values. You can see these are their p-values here, so that the perceived benefits is non-significant. But you can also look at the correlation matrix to see which variables are most highly correlated with each other. So let's see, which one had the highest tolerance? Or the lowest tolerance, rather. Age. So we can see age's relationship with the two other independent variables in the model. So in terms of getting that data, here's an example of the SPSS output, or the SPSS syntax, and it's annotated here to tell you the different options that you can ask for.
I'm sorry, I have a question about the collinearity stuff.
Sure.
So if you're looking at before you run your regression and you run your tolerance, what's a flag for a highly collinear in terms of correlation?
In terms of like the raw correlation?
Yeah.
I don't know like an exact number, but I would think anything that is moderately correlated is
So
something.
anything above like a 0.5.
Or even like, well, moderate in our world is maybe a 0.3 or 0.2, a 0.3 in my mind would be something that I would look at more closely in terms of multicollinearity among predictors.
That's an issue for my mediation model, is that experiential avoidance is highly correlated with my outcome variable, because I have a chunk in that variable that are avoidance symptoms.
Mm-hmm.
So I think that when I looked at per cluster, the correlation was like 0.7
Mm-hmm.
between my mediator and that outcome. That's included in the total scores. I'm looking at total scores. I'm not looking by clusters. So what I'm thinking now is just...
You're talking about the mediator being correlated with the outcome, not the mediator being correlated with another mediator in the model.
Not with the other X, no. It's with the outcome.
And you're saying it's because there's something that's overlapping between the two in terms of measurement?
Mm-hmm. So there are avoidance symptoms in my measure, and then there's this avoidance mediator, avoidance specific mediator.
And because
I
these
mean,
things
they're-
are both measured at the same time,
Yeah,
it's essentially you have like a level of redundancy in what your, between your mediator and your predictor.
And that was one of my reviews, was that, am I measuring different constructs? I mean, there's an overlap, but there is a difference in what these two measures are getting at in terms of, one is more like trait-like and the other is, symptom-specific.
Right.
So,
But
yeah.
the question is it within the person, is it really representing something that's different? I mean, I think it gets to the sort of how tricky it is to test mediation, particularly when you're talking about things that are measured concurrently, which in cross-sectional research, that is, etiological research, that's often going to be the case. But then you're essentially asking, the reader or the reviewer to believe that it's a causal process that you're talking about, really, when you're really looking at two measures of a similar thing in the same, within person. I'm making this face because I'm
No,
kind of
it's
like, I don't know what
tricky.
you do
Yeah,
about
it's
that
tricky.
except maybe not use that variable, or if there's a way.
I'm thinking of taking out that cluster that deals with the, taking that out of the total PTSD symptoms, and then see, I can only say that this mediates re-experiencing and hyper-arousal symptoms and not so much avoidance because there's such an overlap.
Right.
But I have to look at my tolerance for those two.
Well, with the tolerance, though, you're more concerned with overlap
Right.
between
That's right.
among
That's right.
X variables, because then they're fighting for variance explained because they share a lot of the variance that they're explaining is
outcome,
variances
yes.
that they share.
Okay.
Okay. We're just about done. The part that we didn't get to was model building, which is not, you can read it, so I'm not worried. Who uses, just out of for curiosity's sake, who uses like a different type of like stepwise or like a backward forward entry? Who uses more of those like data-driven type regression variable approaches?
It's easy to try in SPSS.
So you do give it a shot to see what happens?
Right?
Yeah. Okay. Yeah, I personally just always do like a forced entry, so. But other people?
Maybe stepwise.
Uh-huh. And do you have like large samples then?
Depends, yeah. Not as large as I'd like, I guess.
Uh-huh. But what makes you choose doing it that way then?
I like to see the separate models and see go from one model, one variable entered, and then the next model, so I can see it. In SPSS, it gives you the table of model 1, model 2, model 3, model 4, so I can see what's happening along the way. So it's kind of like a nice.
But are you asking whether people are using the automated?
I'm asking about the automated, yeah.
Oh, it's
Sounds
But
like
you're saying, yeah.
It's really easy.
forcing
That's
entry.
right.
But I
Yeah,
think
that's
SP
forced entry, right.
I
What?
think SPSS even says that maybe some of the stats aren't as valid or something. I remember reading something in one of the IBM.
Yes,
things.
all of the stats are not valid.
When you do stepwise.
Wait,
right?
what?
Yeah, I mean, it's at best an exploratory.
Yeah, that's what I thought was
Yeah.
weird. When they said that in their like actual help thing. They're like, by the way.
Yeah, they're kind of saying don't do this, but we put it in anyway because our customers demand it.
Right.
I mean, I think if you had have a really large sample and a lot of variables and you truly are exploring, then
Okay.
but there is a full slide on pros and cons of variable entry methods for your reference. Here's the SPSS syntax. Here's the SPS output that's analogous to the SAS output. I know I kind of had a lot to cover today, so if you guys have other questions, just ask me, email me, or ask me after class, okay? Next week, moderation. And if you have moderation ideas, email them to me so that I can post them for the class.